Hello everyone. In this presentation, I'm going to present our paper, EBChain blockchain-based peer-to-peer energy bartering. My name is Abdul Zaki, a PhD candidate at Blockchain University, and this work under the supervision of my supervisor, Professor Dr. Azmir Özkasap at Blockchain University, and the collaboration of Professor Uns Bashir from Zayed University and Professor Walid Al-Khalil from United Arab Emirates University. The content of these slides will be an introduction about the topic, energy bartering and its foundations, and then we'll talk about the prior works and the contributions that we did in EBChain. Then we'll go into the details of the proposed system with the real-life experiments on real-life datasets, and then the conclusion and future work. So with the increase of need in energy, that's like going to be maybe in 2040 about 35,000 terawatt. This is a huge increase in our daily usage of energy. To mitigate the costs and to mitigate the let's say dependency on the grid, people started to use their own energy resources such as solar panels, and a recent study like the solar panels, for example, in the United States are expected to reach about 17 million approximately in 2032. So now we have peers and we have houses and maybe companies or factories with their own energy resources, and that what created what's called peer-to-peer energy systems. So we have in these systems we have, let's say, what's called the prosumer and consumers. Consumers, they consume energy only, and prosumers, they produce and consume energy, and they can, of course, transact energy among each other at this point. Our studies, or let's say in the literature, there are a lot of energy trading, which is you pay for the energy, you got it. And what we work on is energy bartering. So there is no direct payment. You don't pay with money, you exchange it for something else. In those peer-to-peer energy systems, like we have now peer-to-peer network of consumers, prosumers, and we need some advanced and like some suitable solutions for such systems. And blockchain is very useful at this point because blockchain is giving us decentralization. It is a distributed system in which we have also the persistent ledger, and it's also again a peer-to-peer network of, let's say, nodes. Top of the blockchain, we have what's called smart contracts, and smart contracts themselves are, let's say, points or more. We have such rules, and we have, based on those rules, we can do some actions. Like, for example, payment transfer. We can do some other automated actions with those also smart contracts, and they provide us security and trust, because once you have smart contract deployed, if it is done well, you cannot like stop it, and once you have condition met, you can do some action. In the literature, we have a lot of energy trading, and also not only trading, but energy trading through the blockchain. So they use the blockchain and smart contracts to enable this process. However, in other energy transaction types, like energy donation, there are some suggestions in the literature to use, or let's say proposals to use blockchain, but we have not found, let's say, direct blockchain experiments. In our specific case, also for bartering, we have proposed this bartering energy before, and there was no blockchain experiments within that. In our system, or in our paper today, we addressed this point, and we have studied the feasibility of such solutions on a real-life data set. So to summarize our contributions, we can say energy bartering, we proposed EBChain, a blockchain-based peer-to-peer energy bartering system, and we have done some on-chain realization of these bartering processes through smart contracts. And also we developed this simulation platform that integrated those smart contracts with real-life residential data set that we are going to explain. And then we have done some scalability and market behavior analysis. So what is EBChain? Right? We have been mentioned it more than one time. EBChain is, again, a network of peers. Those peers can be houses, they can be companies, they can be factories, and those, they are prosumers and consumers. So some of them need energy, some of them have energy, and they trade energy among each other, or barter it. That's what they have in the system. Also, they also exchange transactions based on their, let's say, trading. The EB chain proposal or the smart contracts that we have within EBChain, they match between the people who needs energy and the people who, let's say, would like to sell their energy. And they do the same also for bartering. So they do the matching for bartering and trading at the same time. So in more details, or if we'd like to talk about the system like characteristics, we assume we have M peers in the system. Each peer, again, is a prosumer or consumer at a specific time step, not through the calculations. And then each peer is equipped with a battery capacity CI. Each peer has his own battery. And we'll see in a moment why we need batteries, because it's a characteristic of the bartering algorithm that we have. Also, we assume that energy can be exchanged between any two peers without transmission losses, and we have just disregarded the energy charging, discharging, and degradation effects on the batteries. So the system itself is using what's called peer-to-peer energy bartering algorithm that we have proposed in a previous IEEE ICC paper. In this system, or let's say in this algorithm that we have proposed, we have a prosumer with excess energy, and this energy will be bartered. How it's going to be bartered? So part of this energy will be stored on the consumer's battery. This is stored, not used for now. And another part of this bartered energy will be consumed by the consumer. So what we did in this proposal is we said, okay, this consumer, he needs energy, he cannot buy it, and he's going to use it now. He's using fraction of this bartered energy. But in exchange of you letting that prosumer to let him, let's say, utilize his battery for a specific time step. So what's the benefit for prosumer so far? The prosumer will be trying to sell this energy that he stored on that consumer energy in the next time step. So this is the algorithm description. I'm not going to go into much details because this is another paper. Let's go to the actions that we have on EBChain. So again, we have sellers, buyers, barterers, and we have the utility grid, of course. It's not an active on the system itself, but like the system interacts with it. We have the blockchain, and on the blockchain, we have what's called the smart contracts for the energy bartering. So if we go step by step, this system goes this way. So we need people who would like to submit their wishes, what they would like to buy or let's say trade or something else. Based on those requests, the smart contracts would calculate the price, the peer-to-peer price, and then it would start trading with the previously bartered energy, those that are on the batteries, and then it would initialize the barter trading with the current energy offers. And after that, we do the bartering. So if we have any energy left that was not sold, we do energy bartering. If we have, after this point, if we have an energy offered remained, what we do is we sell it to the grid. And at the end, what we do is if we need, let's say, any energy that was not met from the peers, it's bought from the grid. After that point, like the smart contracts, they do what's called emitting events, and those events, they can be listened to by the other entities. So the entities will be listening to those events, and once there is an event, they can do real life transactions based on that. So we did again an analysis of the system. So we have, let's say, the pricing. Pricing is a topic by itself. It's very well studied in the literature, and it's again a wholly full research topic. So what we did in the pricing to not make it affect the results too much, or to not, let's say, go into deep details with it, we just did fixed pricing per time step based on several criteria. And in short, this pricing would give us a price that's better for the prosumers and also better for the consumers. So prosumers can sell their energy at a price that's higher than the feed-in tariff. The feed-in tariff, it's what the utility grid would buy energy from you. It's the rate. And also the consumers will be buying energy at a rate that's lower than what they would generally pay the utility grid. So that's like in short. For the used data set, we use what's called Australia data set. It's a set of 300 houses in Australia that they measured in real life their energy consumption and energy production. Again, based on in our experiments, we did 10 runs. Each run is 1 week. data set. We used the for the local blockchain network, followed by etc. for the technical part. So if we go to the results that we have gained, so if we check the gas consumption and execution time, not latency, through the different system sizes. System size means we have 10 peers or we have 100 peers, etc. So first of all, we can see the total gas in blue that it's increasing approximately linearly in an expected manner, as we can see. What we can conclude is this energy, or sorry, this gas consumption, it is kind of expected. So it's not, we don't have some exponentially, let's say, consumption at this point. And again, these results are for the whole week. It's not per time step. Another point in here, we can see the latency also. The latency also increases with the system size, but we can see it's kind of to 100. It's kind of acceptable latency. But after that, it would be a bit maybe slow in matching. It might suggest for us that this system is suitable for only microgrid scales, not full scales. If we take the how many energy was traded and how many energy was bartered, that also we can see from the results. So check again, this blue line is the let's see it's increasing with time. So we have more energy being sold and bought in the system with the increase of peers. On the other hand, we have the energy bartered. It is a bit like, how to say, the highest at small scale, 25, let's say, houses, and it is lower than that in, it started going lower and lower. And this is due to the nature of the algorithm itself, that because we prioritize trading, and the more trading we have, the less bartering we will have. If we go and check also the total, the amount of energy itself that was traded. So we have two sources, either from selling energy directly or from the energy that was bartered and stored on the batteries themselves. And we can see we have from both. And again, this is just aligning with the previous figure, the amount of energy that is sold from the bartered one is going lower and lower. This is logical. However, this figure just shows that energy is getting traded from those bartered one. That's good for the prosumers. Finally, if we check the peer participation and market activity, we can see again in here we have increased bartering requests. It's increasing all the time. The only thing that goes not with the whole figure is the buyers and sellers, they increase till 200, and then we can see that there is a huge decrease in that. This is the number of peers who participated in operations. If we check the events themselves, like how many bartering requests we had, how many selling requests we had, we can see this figure, and we can see that a lot of bartering requests exist in the system, and also for the buying and selling requests, they are kind of balanced among each other. So to conclude the contributions and results, we can say that we proposed a blockchain-based system for energy bartering. Also, we integrated this peer-to-peer energy bartering algorithm, and we have realized it through smart contracts to do the selling, buying, and bartering operations. And we evaluated the system itself using a real-life dataset, also grid, with scalability analysis. And we have seen also like linear gas growth to indicate predictable scalability and feasible decentralized energy. We can, let's say, incorporate realistic battery models, and also, let's say, include the charging efficiency. Also, what we can do is account for battery degradation and make maybe some degradation over compensation. Also, we can include a network effects in the system, because in the system we have now, we didn't study these parameters like the delays and transmission loss in energy Also, we can develop market conditions because, as we have seen, we have directly trading, then bartering, and this affects the results. Finally, we can deploy this EBChain on different systems, and we can study its behavior because we deployed it on Ethereum and EVM, let's say, compatible blockchain. Thank you for listening. If you have any question, just don't hesitate to send me an email.